Good day, ladies and gentlemen. Welcome back. This is going to be continuing to chapter 4 on operations on data. But before I get there, I just quickly want to officially welcome you back after the lockdown. Or how should we say, are you really back? Well, as you probably have taken notice from the universities that we are only back online. But before we continue, I just feel from the bottom of my heart to just ask you all, I know you cannot reply with this recorded lecture, but how are you? I just want to tell you a little bit about how I feel perhaps. I think I'm okay, and my family, we are protected during these challenging times. But again, how are you really? I know that some people have desperate and dear challenges. I know some people don't have income at the moment. I know some people have really a lot of issues. All that I really can say to you, and it's my wish from the bottom of my heart to just say to you, hang in there. This too shall pass. This is not something that's going to last forever, so don't let it get to you. I know people are talking about this new normal, but please um, don't let it get you. It will actually get better again. All right. So and also just what if you do get sick? Well, I just want to say to you, do not panic. You will be okay. Us young people and people with strong immune systems and so on, we will be okay against these viruses. So don't worry about it. You all know that really, although this is a highly infectious thing, and you probably know this, but I just want to reassure you, you will be okay. If you are struggling to cope with any of these issues, I want to tell you that my door is open. Please talk to me. Send me an email, send me a WhatsApp. Uh, I will, to the best of my abilities, try to also talk to you. So I really want to invite you, if you really just need, even just from a friend perspective. No, I will not be your lecturer, but I really just want to tell you that if you really feel the need to talk to someone, but you cannot talk to anyone else, talk to me. My door is open for you. Okay. What about the other people? Um, you know, all that I try to view other people is also to say, well, I might have my own problems, but I know it's almost always certain that there are other people with much worse problems than you. So if you can, lend a hand. If it is just to say a word of encouragement, do so. That costs nothing. I once heard someone say, you know, what costs nothing, but it's the most expensive thing to give away, and that's time. So my philosophy, and people, I do respect people with other religions, but I just want to tell you that, this has happened in my life, and I can just tell you that listen when God talks softly to you, and obey before God starts to talk hard to you, and then you will have to listen. All right, so with that said, let's just quickly look at the administrative issues here. So again, welcome back, and I hope we can continue, even if it's only this online nature, continue and finish off the semester successfully. I believe it's in every university lecturer's mission to try and still give you the necessary guidance and the necessary lecturing to try and help you through this difficult time. So how will things happen from now on? Well, as you've learned, everything will happen online from now on for the entire rest of the semester. It might even go on further than that, but these are uncertain times. We don't know what to expect. So again, If things change, we cannot control that ourselves. We can control the things that happen to us now and at this moment, but we can't control the future. So don't let it get to you. Okay, so for the lectures, I'll say a little bit more on the next slide. For the practicals, it will also continue online. There's some practicals still outstanding, and we will probably only have another one, maybe two practicals for the remainder of the semester, just to make things a bit easier for you as well. Semester test 2 is coming up. You'll notice that that's really only at the end of the semester. The new university calendar I'll put up. I've also put up the new study guide, the updated study guide. I'll say a bit more about that. Then if you were sick for the first semester test, or if you will be sick at the second semester test, there will be an opportunity for a sixth semester test. Look in the study guide. People, I just want to give you a little bit of a heads up and warning here. Don't just try to stay away from the test if you're not really sick. Because you will write the sick test about the content for the first and the second semester test. So please try to write the first, try to write the second semester test. Don't miss it just for any reason. And for the exam, also the exam will be online as well. All these things, as the tests and exam, will be open book, online, click up tests. But please, people, I also want to warn you a bit there. Don't think that you cannot study or don't have to study for a test. Still counts 70% of your semester mark, the semester tests. The exam, it counts a lot. All right, so study for it, because we won't just ask questions that you can verbatim copy from the textbook. You will still have to study and know your work. All right, if you're going to frantically page around to find an answer, you're just going to waste your own time. Also, the mode of the test and the exam will also differ from now on to cater for dishonest people. Unfortunately, those people will always be there, so that people cannot copy from each other. Also, random questions will be posted to each student, and you'll only be allowed to look at a question, complete the question, and press submit for the next question. You won't be able to go back to previous questions and so on. This is all just in trying to make sure that students stay honest. And don't worry, I'll give enough time for you guys. All right, so don't worry about these things. I have bounced all these new regulations, so to speak, with how you will do the test. I've bounced it with the head of department, and the head of department also okayed this. So please bear with us. But you will have enough time. Don't worry about that. Still, if you want to ask any queries, the official channel is still COS151 queries at cs.up.ac.za, and the website will mainly be the ClickUp website from now on. So all announcements and all further submissions and so on will happen on the ClickUp website, not on the COS151 computer science website anymore. In terms of how we will lecture, so we will use the flipped classroom approach that we've already started doing just before the lockdown, where lectures will be released before the time, approximately about 2 days before the time. In other words, this recorded lecture you're listening to now. So please review the lectures yourself before the official lecture time starts, because during the official lecture time, which is for this particular set of slides, is going to be on Monday, 4 May at 8:30, where you will log on to ClickUp and go to the Blackboard Collaborate link, and there you can then go and ask questions. It will mainly be a question and answer session. Perhaps I will do a bit more explanation if I see some questions about some of the concepts that you might not understand. And this will also be recorded, so that students that for whatever reason did not attend can actually attend it later, or can actually watch it later. But please note, we will still keep class attendance. So please make sure that you do attend the lectures. It's taken automatically by the system. And as I said before, the study guide is updated and available. It's uploaded to ClickUp, so please go and look at the updated study guide, specifically in terms of the new dates. I've indicated in the study guide where all the changes are. If there's any more questions or something I didn't ask or didn't cover now, please feel free to ask. Send an email to COS151queries@CSUPACZA, or ask it during the official class time. Let us now continue with the lecture. So chapter 4 is about operations on data, and we are going to cover this during this week as well as next week. So I've scheduled enough time so that we don't have to sit too long to listen to these lectures, and split the work up so that it is so that we can cope with it. So in chapter 3, you'll recall that we discussed the fact that data inside a computer is stored as a pattern of bits. We know this by now, just zeros and ones that are stored. Now, we can do operations on these bits, and we call these operations logic operations. And we refer to those operations that apply to the same basic operation on individual bits of a pattern. In other words, we can have operations on just individual bits. So we take this bit and we have another bit and we do an operation on that. Or we can do operations on two corresponding bits in two patterns. So you will see in the examples just now what we mean with that. What we basically, the terms we use to say to that, to describe that, is that we can define logic operations at the bit level or at the pattern level. So basically, if you have a bit pattern like this, then basically what we say, if we do operations on the bit level, then basically we can do an operation between this bit and that bit, or perhaps between this bit and that bit, or perhaps between this bit and that bit. So this is basically at the bit level. But we might even have a pattern level, so it basically means that we might have a bit pattern that looks like this, 0, 1, 1, 0, and maybe 1, 1, 0, 0. Then basically we say we can do it at the pattern level, because we say that this is a bit pattern and that is a bit pattern. So basically, to then say between the two patterns, we can now do some operation between this bit and that bit. So in other words, between the first two bits. Or we can do an operation between that bit and that bit. In other words, between the third bits of each bit pattern, and so on. So that's the difference what we mean when we say on bit level. It's literally doing some combination of comparisons between the bits in the same pattern like this one here. Or on pattern level, we basically say that we're doing comparisons between these two bits, or those corresponding two bits, or those two. All right. In this case, we only had two 4-bit patterns, because each bit pattern consisted only of 4 bits each. So logic operation at the pattern level is n logic operations of the same type. So that's what I just tried to say here. So if we have in this example here 4 bits here, and in the next one also 4 bits, then we basically do a bit level operation between the corresponding bit pairs, like for example between this pair or that pair or that pair or that pair. So logic operations at bit level. So let's first look at these logic operations at bit level. In other words, we have a single bit pattern. So a bit pattern, in other words, a number of bits next to each other. Now, a bit can take on the two values 0 or 1. You know that already. If we interpret 0 as the value false and 1 as the value true, then we can apply the operations defined in Boolean algebra to manipulate bits. What do we mean with that? Boolean algebra, by the way, the word Boolean is basically coming from George Boole. So that's the guy, George Boole, came up with this idea of Boolean algebra, and it belongs to a special field of mathematics called logic or logic operations. So in this section we show briefly 4-bit level operations that are used to manipulate bits, and these will be NOT, AND, OR, and XOR. So we're quickly going to look at those. If you want to look a little bit more in detail into this, Appendix E will give you some more examples and discuss it in a bit more detail. For the purposes of this course here, we're only going to look at these 4 logic operations, and I'm just briefly going to describe everything on this slide. The next 2 slides give a bit more details, but I will have covered that already. So NOT is very easy. You have done that before, actually, when we did, for example, a ones complement operation. Remember what was a ones complement operation as we discussed in chapter 3? For example, if we had the bit string 10110, if we do a ones complement on this bit pattern, then basically we take each bit and we flip the bits. In other words, a 1 becomes a 0, a 0 a 1, and so we continue. So this basically is the ones complement representation of the original bit string. Okay, so, and this is basically the operation, the NOT operation that we do. For example, if we say not x, now if we consider x in this case can only be a 0 or a 1, as you know by now. So not x or not 0, if it's not 0, then it's basically 1. Or if it's not 1, it's 0. So you can see it's just flipping the bits as we've done before. Now if we look at OR, then basically OR is the only, well, sorry, let's just go back to NOT. NOT is the only operator here that we call a unary operator. Unary means 1, which means the NOT operation operates only on a single bit at a time. As you could see, not 0, that gave us 1, and not 1 gave us 0. All the rest, this is for AND, for XOR that we're coming to just now, and for OR. For all of those, you need actually 2 inputs. In other words, OR and an XOR are called binary operators because they operate on 2 things. There's 2 inputs, where with NOT we only had 1 input. So let's quickly do this. If we look at the OR and we say X or Y, in other words 0 or 0, will still give you a 0. 0 or 1 gives you a 1. 1 or 0, just in reverse order, still gives you 1. And 1 or 1 gives you a 1. So most of us know this by now, where AND, the AND operator, basically says 0 and 0 still gives you 0. 0 and 1 gives you 0, because basically whenever there's a 0 involved in an AND operation, the result will always be 0. So in other words, just the other way around, 1 and 0 still gives you 0. The only thing that gives a 1 with inputs in AND is when X is 1 and Y is 1, then it will give you a 1. The XOR operator, you'll see a little bit later, is actually a combination of some of the concepts of both the NOT AND and XOR. The NOT, the AND, and the OR operators. and you'll see what I mean with that later. But with XOR, the easy way to remember this is that XOR is a so-called difference checker. What do I mean with this? In other words, it checks the input. If the two inputs are both different, then the output is a 1. But if they are the same, the output is a 0. So let's quickly look at the table for XOR. If the two inputs here is a 0 and a 0, they're the same. So in other words, the output is a 1. If the output is different, if the input is different, in other words, a 0 and a 1, if those two are different, then the result is 1. You can see, that's why we call it a difference checker. Or if the input is 1 or 0, they are different, then the result is 1. If the input is 1 or 1, then basically they are the same again, so the result is 0. So every time when the two inputs are different, like in this case here, the two inputs are different, then the output will be 1. And in the other two cases, like these two cases here, if the inputs are the same, like 0 and 0 or 1 or 1, then the output basically is 0. That's how you can remember it. It's a difference checker. So everything I've said now basically contained into these two slides. So I'm not going to go through these slides. You can go and look at them yourself. Let's look at an example. And this example is just a very basic, simple English language example to prove that sometimes we are not very accurate when speaking and there might be a bit of confusion. For example, in the English, we use the conjunction or sometimes to mean an inclusive or, and sometimes to mean an exclusive or. What do we mean with this? Here's the two examples. In the following sentence, I wish to have a car or a house, uses the or in the inclusive sense. So that basically means I wish to have a car or a house or both. All right, so technically we know this is not correct. Technically the next one is correct. In this sentence where we say today is either Monday or Tuesday. You see, it's either or. It uses or as well, but in this case, it cannot be both things. It can only be one thing. There's no way that today is Monday and tomorrow is Monday. That can never work. So in this case, it's pretty clear that today is Monday or tomorrow is Tuesday. But we can't say today is Monday and tomorrow is Tuesday. All right. So as I said to you before, this is the easy way to remember. The exclusive or is basically the difference checker. So if the inputs basically are different, the output is 1. If the input is the same, in other words, either two zeros or two ones, then the output is 0. Let's look at this example. So the XOR operator is not actually a new operator. Remember I said that to you a few slides ago. We actually make use of a combination of and, or, and not, those other three operators. But we use a combination of all of those to simulate the XOR operator. For example, we can say X XOR Y will give you the same result as this very long equation here, which says first we do X and not Y, or not X and Y. Now, to try and illustrate this to you a little bit, I went and created a truth table. The truth table looks as follows, and I'm trying to explain it to you as follows. For the moment, just ignore that. I should have deleted that from the slide, sorry. So here I have created the truth table. In other words, I have created the native X and Y inputs. So basically I've created all possibilities when X could be 0, Y could be 0, 0, 1, 1, 0, 1, 1. Okay, so there's all the possibilities, all the combinations of zeros and ones that you'll ever find between X and Y. So now, to try and get to this full equation there, we can go and break things up a little bit more. Now we can just follow normal mathematical practice. We have this square brackets here, which basically says we should do that first, and there, and inside the square brackets we have two normal brackets, which means within that square brackets we have to do that first, and so on. So let's see, the first things we need to try and figure out is what is not y and not x. That one over there. All right, so this is what I have here, not x and not y. So now we simply just say not x, so we take x, not x, in other words, not 0, which we know what the not operator does, it flips the bit. Not 0 is a 1. Not 0 is a 1. Not 1 is a 0. Not 1 is a 0. And so we do the same for not y. There, the not 0 is a 1. Not 1 is a 0. Not 0 is a 1. Not 1 is a 0. Okay, so now we basically have completed this operation here and that operation there. But there's other things to do still. Now we must take, for example, this operation here and that in other words, this input here as an input and that as an input. In other words, we're basically going to say what is x and the result we got from not y. So in other words, we check what is x and the result of not y. This one over here. So we basically just do this column and it with that column. So 0 and 1 gives us 0. 0 and 0 gives us 0. 1 and 1 gives us 1. 1 and 0 gives us 0. And similarly, we do this operation here with this, if I can use this symbol here, this operation here with this input and that input over there. In other words, we check what's the result of not x and y. In other words, again, we look at the not x column here and y. So it's basically these two columns. We do an and between them. So 0 and 1 gives us a 0. 1 and 1 gives us a 1. 0 and 0 gives us a 0. 0 and 1 and 0 gives us a 0. And now we basically have completed basically that in this column over here, and we have completed that in this column over there. Okay, so now all that remains is to basically say what is this operation and that operation there, what is an OR. In other words, we OR these two columns with each other. So we say 0 or 0 gives us 0. 0 or 1 gives us a 1. 1 or 0 gives us a 1. 0 or 0 gives us a 0. And now you will note that the final output between this entire operation over here is exactly the same as the exclusive OR operation. 0, 1, 0, 1, 1, 0. Right. So this is basically a way of simulating, using the other three operators, how the XOR operator works. All right. And this is how far as we're going to go with these four basic operators. We can now simulate anything else using these 4 operators. Right, so just also about logic operations on pattern level. So we've just discussed it on bit level now. Now on pattern level, we're going to use the same 4 operations, NOT, AND, OR, and XOR, and it can be applied on an n-bit pattern. So the effect is that in the same way as applying each operator to each individual bit for NOT. So in other words, if it's the NOT operator, we do it on individual bits, unary. Remember, NOT is a unary operator. Only has 1 input and it will give you 1 output. Good. All the rest, the AND, the OR, and the XOR, you will see that basically we give 2 inputs and we get only 1 output. Same for XOR, 2 inputs, and for OR and also for XOR, 2 inputs, and all of them will give you 1 output. So let's do some examples of those as well. So we're going to use NOT, the NOT operator, on the bit pattern 1001, 1000. Right, so it's this here. So as we said before, we know this is very similar than we've already done, what's exactly the same as a ones complement operation. We simply flip every bit. So there's the original bit pattern over here, and you see then a 1 becomes a 0, a 0, a 1, a 0, a 1, a 1 becomes a 0, 1, a 0, and 0, 1 becomes a 1, 0 becomes a 1, 0 becomes a 1. So we just flip every bit to get the output. And you can see, although this is only one, we only need 1 bit pattern to get to the output for the NOT operator. For all the rest, in other words, for the AND, the OR, and the XOR operations, we need 2 inputs, like for example input 1 here and input 2. Let's just see what the example says here. The example says use the AND operator on the bit pattern 10011000 and this bit pattern here 01101010. So there are they, the first and the second input, and then basically we do a corresponding AND between each bit pair between the 2 inputs. So we first say what is the output of 1 and 0 gives us a 0. 0 and 0 is 0. 0 and 1 is 0. 1 and 0 is 0. 1 and 1 gives us a 1. 0, 0 gives us a 0. 0 and 1 gives us a 0. And 0 and 0 gives us a 0. Alright, so there we did a pattern operation of AND between these 2 bit patterns. And we did it every time for the 2 corresponding bits until the very last one to get to the result, the final output here. This next example says use the OR operator of the bit patterns, this one over here and that one over there. So there are the 2 bit patterns exactly written over there. So in the same way that we did with AND in the previous example, we do OR now. 1 or 0 gives us a 1. 0, 0 gives us a 0. And so we continue with each one until the end. 1 or 0 gives us a 1. And so the final output, basically between the 2 inputs, again, corresponding bit to corresponding bit every time until the end to give us the final result. The next one, use XOR, the XOR operator, on the bit patterns this and that. Right, so again, there's our 2 inputs, this and that. And now remember, the easy way to remember the XOR operator, it is a difference checker. It finds out where are the difference between the two bits? So is there a difference between 1 and 0? Yes, there is, so the result is 1. Is there a difference between 0 and 0? No, so the result is 0. Is there a difference between 0 and 1? Yes, so the result is 1. There's a difference, so the result is 1. These two are the same, so the result is 0. Different, the result is 1. Different, so the result is 1. Different, so the result is 1. All right. Later you'll see where we're actually going to use these, and it's going to be used for doing some calculations. But for this lecture, we're just looking at the basics now, just so you can understand how these basic operators of not, and, or, and XOR work. Right, so let's look at some applications, how you might actually want to use some of these operators to change some of the bits, to modify them basically. We can use it for complementing. Now we're not going to do that in an example. We now already know that when doing a ones complement, that's basically what we do. We flip the bits, and we do that with the not operator. Now we're going to use and to do so-called unsetting, or we're going to do so-called setting, and XOR we're going to do flipping. Now don't be confused now. Flipping means flipping the bits, but it is not the same as with complementing in this particular case here. Flipping here is something different. In other words, here complementing is we're doing something to try to modify those bits. Flipping is basically to have the final result. And I think the easiest way to do this are with examples. So again, we're not going to do an example of not. You know what not does? It flips the bit. So let me just quickly give a quick example here. So if the original input was 1011, then the final result, or the result of this, would be 0100. Each are being done on each particular bit over there. Let's look at what we mean with unsetting, setting, and flipping. And what you just need to remember here is that when we say unsetting, you must remember and. When we say setting, you must remember or. When we say flipping, you must remember XOR. So it's just in terms of the words we use in the problem will indicate to you what operator you will use. So again, if we say complementing, we use not. Unsetting, we use and. Setting, we use or. Flipping, we use XOR. You just learn this by heart. So here's an example now that says use a mask. We'll explain what a mask is just now. To unset. So unset, all right. We remembered that when we said unset or even clear, then we actually mean it means we're going to have to use the AND operator, as you see here. Okay, so use a mask to unset the 5 leftmost bits of a pattern. Test the mask with this bit pattern here. So all that they're basically saying is we must do something to clear the first 5 bits of this bit pattern over here. To clear or to unset it just means to make everything 0. To set something, in the next example you'll see, is to make everything 1. Or to flip, as you will see in the last example, is to make a 1 a 0, a 0 a 1, etc. Okay, now remember that we said using unset, we know that we must use the AND operator. And we know by now that the AND operator requires 2 inputs. It requires these 2 inputs. The first input is this one given over there, and the second input is the mask. In other words, we must come up with the second input ourselves. And to do this when doing unsetting is basically to make everything that needs to be unset zeros in the mask, and the rest that does need to have that needs to stay the same in essence, we're simply going to make all ones. That's how easy it is to remember. And then we simply do the bitwise AND operation between each and every of these bits. So 1 and 0 gives us a 0. 0 and 0 gives us a 0. And there you'll basically see you can continue. So because we made all of these zeros, the result will inevitably be 0. Doesn't matter whether there is a 1 or a 0 or a 0 there. Everything will be made 0 due to this AND operation. In other words, basically unsetting or clearing what we are doing here. But this, the problem set only on the 5 leftmost bits. So if we say in the problem to unset the 5th, 6th, and 7th bit, then it would have meant that we had to go and change these 3 bits. And then you had to make your mask, in this case, all zeros, and the rest of it would have been all ones in this example I'm giving here now. All right, because if you look at the rest, while you kept all of these last 3 things all ones, as you can see, 1 or 1 would give you 1 and 1 would give you 1, 1 and 1 would give you 1, and 1 and 0 would give you a 0. So in essence, 110 is the same as the original 110 there. You didn't change anything. You only had to change the first 5 bits in this example. So this was unsetting or clearing bits. All right. So in practice, you might want to do this. You might want to enter a value in memory, and there might already be a value in memory. Some arbitrary value or whatever, like in the example they gave you here. And you need to reset the first 5 bits to 0. In other words, unset them, and this is the way with this AND operation to do this. In the next example, we do the following. We use a mask to set in this case, not unset. All right. When we set, it means we want to make those bits all ones. So if this is the original bit pattern, same as the original bit pattern in the previous example, now it's just the other way around. In the previous example, with unsetting, we had to, in the mask that we want to unset, make everything zeros and the rest ones. Now, if we want to set the 5 leftmost bits, now it's the other way around. We make everything ones instead of zeros, and the rest we make zeros instead of ones. Okay, so you can see for OR it's just the opposite. So here we take the original input, this that we found there, and the mask we had to devise, where we know we had to make to set it, we have to make all those ones ones, and not to touch the rest, we just make zeros, and we use the OR operator between each of them. So we'll say 1 or 1 gives us a 1. So we've set that one. 0 or 1 gives us a 1. 1 or 1 gives us a 1. 0 or 1 gives us a 1. 0 or 1 gives us a 1. And the rest remains unchanged. 1 or 0 remains a 1. 1 or 0 remains a 1. 0 or 0 remains a 0. So we can see effectively we haven't changed those. We only have changed those first bits. In other words, this all to 1. And then very lastly, in this next example, we are going to say use a mask to flip the 5 leftmost bits. And when we have to flip bits, in this case, we know that we have to use XOR. Right. So we take the original pattern and we have to devise some mask here. And the mask in this case is going to be the same mask as we used with OR. All right. So the mask is the same. as you can see in the previous example, everything that we want to flip, we must put ones, and everything that we don't want to flip, we must put zeros, and then simply use the XOR operator. Remember, the XOR is a difference checker, so it tries to see where are the two things different. So let's again bit by bit check them. Are these two things different? No, they're the same. So the result is 0. Are these two different? Yes. So the result is 1. Are these two different? No, 0. Are these two different? Yes, 1. 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 Are these two different? No, 0. So in effect, you can see the original part 110 stayed the same as 110. We didn't flip any of those bits, but now look at the result here. We have flipped every bit from this to what we see originally. See, now it's a 0, it was a 1. Now it's a 1, it was a 0. Now it's a 0, it was a 1. You see, every time it's just flipped the bit by using the XOR operator. All right. And